Okay, Chapter 2, Section 8, one-to-one functions and their inverses. So in this section, we're going to cover one-to-one functions, the inverse of a function, finding the inverse of a function, graphing the inverse of a function, applications of inverse functions. Okay, so the inverse of a function is a rule that acts on the output of the function and produces the corresponding input. Okay, so the inverse undoes or reverses the function, whatever the function has done. So for instance, we're talking about cases like this. So for example, a quick little example. Say we have f of x is equal to 2x plus 1, right? What does this mean? This means that whenever we input a value, or that input is, whatever we input into it, we're going to double it and then add 1, right? That's what this set of instructions tell us. Double the input and then subtract and then add 1. Then add 1, and then out will come out your output. Right? Something goes in here, we do this to it, right? The function, these are the instructions for your function, f, double the input, then add 1, and out comes the output. What we want to do is to be able to reverse this process. We want to be able to take this output from here and plug it into some other function, some new function. Let's insert it in here. New function, such that the output of that function, when you input this input, it'll bring you right back to where you started to give you the same input. Right? So this should be true for, just to pick a number for this process. Let's say I input an 8, right? I input an 8. I know that this function is going to double it and then add 1, so it'll be 16 plus 1. I know the output of plugging in an 8, that output should be a 17. And then I take that 17 and I plug it into this new function that will undo whatever this did, right? Double it, add 1. So it's going to subtract and divide by 2, whatever. Okay, so then when we do that, it brings you right back to where you started. It brings you back to 8. And that should be true. That little loop should exist for all values for where the function f is valid, right? So any input you can put in here. Now, given this particular one I chose, it should be all real numbers, right? So for any real number you put in here, you should be able to get out a resulting output, and then you plug that into this new function, and then that new function will undo this and bring you back to here. So this new function here is the inverse of this one, right? That's what it means here. The inverse of a function is a rule that acts on the outputs of a function and produces the corresponding input, right? So they will undo each other. That's what inverses are. We've run into this word inverse before in a different context, but slightly different context. But the word inverse, we ran into operational inverses. So for example, we know that if we take some value x, doesn't matter what it is, and we add 3, then what we could do to undo this process, to undo this plus 3, we know that we can subtract. Let's put it in, right? We can subtract 3, right? So the operations of addition add and then subtract. So the operations of addition and subtraction are inverse operations. Inverse Likewise, multiplying and dividing are inverse operations, right? They undo each other. That's what we're talking about here, except we're specifically talking about functions. We're going to be given a function, and it's going to be our task to determine, first of all, if that function qualifies as a function that can have an inverse function, because not all functions can have an inverse function. Not all of them will, not every function will be capable of having a new function that will undo it, right? So not all functions can be undone, I guess, another way to put it. So first of all, we have to decide if it's a function that can qualify to have one of these reverse functions, inverse functions exist. Next, we might be asked to find that inverse function. Next, we might be asked to confirm that it works. And then next, we're going to be asked to graph them and see what relationships exist between them. Right? That's what this section is all about. So the first task is to determine when a function qualifies to have one of these inverse functions exist, right? So not all functions have inverse functions. Those that do are called one-to-one. In order for a function to have an inverse function, to be deemed worthy of having one, it must be a one-to-one function. So let's talk about that. What does that mean? What is a one-to-one function? How do we know if something is a one-to-one function? So one-to-one functions. If we go back to these jelly bean style descriptions of mappings for functions, we can see what a one-to-one function is. So on the left here, we have one function, f, right? So this purple jelly bean describes the domain of f. This is the domain of f. And then this blue one here is describing the range of f. Range of f, right? So then the arrow is the operation that f takes. I don't know, maybe it's multiplying the input by 2 and adding 2, or maybe it's multiplying the input, maybe squaring the input and dividing by 7. I don't know. Some operation is happening from there to there. And it might be a rule that can be described by an equation. It might be a rule that can only be described by arrows and connecting them. There might not be a mathematical equation that describes the input and how it connects to the output, right? I mean, these might not even be numbers. We could have names of students in my class and then letter grades, and then I just connect them. That could be my function. Okay, but typically we deal with cases where we have numbers, and typically we deal with cases where the rule of how to go from the domain to the range, the rule is some sort of consistent equation that can be applied for the input, right? Some sort of input-output situation. At any rate, what we want to draw from this is that this is describing that the domain has the numbers 1, 2, 3, and 4. The range has the numbers 2, 4, 7, and 10. And that the 4 leads to the 10, the 3 leads to the 7, the 2 leads to the 4, and the 1 leads to the 2. Okay, that's this function. Now, in contrast, looking at this function, this is the g function. So this purple jelly bean over here is the domain of the g function. Domain of the g function. And this blue jelly bean over here is the range of the g function. Range of the g function. So the g function has in its domain the 1, the 2, the 3, and the 4. And the g function has in its range the numbers 2, 4, and 10. Okay, so more specifically, the 4 is being mapped to the 10, right? The 3 is being mapped to the 4. The 1 is being mapped to the 2. In notation style, we can also say that for here, this is f of 4 equals to 10, f of 3 equals to 7, right? F of 2 equals to 4, and then f of 1 equals to 2. Right? Over here, we have that g of 4 equals to 10, and g of 3 equals to 4, and g of 2 equals to 4, and g of 1 equals to 2. Okay, so just a different notational style that describes the exact same thing. Okay, the difference between these two functions is that for the f function, every unique value in the input, every unique value in the domain leads to exactly one value in the range that's required for a function, right? In a function, every single value in the domain is mapped to a unique value in the output. That's a function. So both of these are functions. Every single input value is mapped to one unique output, right? When you input a value into a function, you have a specific answer. It's that result, one unique result. You don't have ambiguity of like, well, it could be 7 or it could be 9. You have one unique output for every input. So both f and g are functions. However, a function allows this right here. A function does allow for a unique number, two different numbers in the domain to map to the exact same value in the range. That's allowed for a function. But that's what we want to avoid when we want to identify functions that can be reversed, functions where the inverse will work. When we avoid this situation, if we can come up with a function that doesn't have this, where this doesn't happen, those functions that are called one-to-one. So that's why this one, f, is a one-to-one function, and g fails to be a one-to-one function for this very purpose. Remember, this whole section, this whole chapter, is about being able to undo our function, right? We're going to have some sort of a function. Let's describe it this. So we had some function f of x, and so we're going to have some sort of input come, right? Some input goes into here, input, and then we had some sort of work for our function, whatever that does. It's some sort of some sort of influence from the function onto the input. We double it, we triple it, add 7, divide by 9, whatever we do, and out will come out the output from here, output. But then we want to be able to come up with a new function where we take this output, we plug it into this new function, and then that function will undo whatever this did, and then out will pop out the exact same input, right? That's our goal. But if we see we have a situation where more than one number leads to the same output, right? So we have a case where maybe we plug in a 4, right? We plug a 4 into here, and out will pop out a 10. And then we take that 10 and we plug it into here, and well, hopefully, if things work out, it leads me back to 4, right? It's a nice, perfect little circle when it comes to the 4 and the 10. But we have a problem when we deal with the 2 and the 3, because we have a function where both the 3 and the 2, both of them lead to the number 4 as the output. Perfectly okay for a function. You're allowed to do that. This is the g function. Oops. We have two different inputs into the g function that lead to the value of 4. But then when we want to go backwards, okay, we take that output and then we plug that into this 4. This 4 goes into this new function. It should undo that. But then where would it go? Would it go to the 3 or would it go to the 2? Right? It's ambiguity, right? So the reverse is no longer going to be a function whenever we have that situation. So this right here is what ruins it. This g function cannot qualify as a function that can have an inverse function because of this very thing right here. Okay, so in order for a function to be a function that can have an inverse function, it must be the case that every single output, every single value in the range is the result of a unique value in the domain, right? One output leads to one and only one value in the range, and every value in the range is the result of a unique value in its domain. That way we can send it back, right? You can think of it that way, kind of visualize, kind of tossing the ball this way, and then you're like, oh, let's send it back. So we can just bring it back to there. So the 3 lobs over to the 7 can toss it back to the 3. The 2 can toss it back to the 4 can toss it back to the 2. But if we have this sort of a situation, the 3 gets lobbed over to the 4, the 2 also goes to the 4, so when we're trying to lob it back, which path do we take, right? The 4 won't know whether to go back to the 3 or to the 2. I know you're thinking, well, maybe can we do some sort of conditional patchwork thing of like, you know, sometimes it goes to 3, sometimes, I know, but we don't want to do that. That might be some sort of overly complicated way of patching it, and that's not what we're interested in. So when we run into this, we're not going to try and fix it. We're just going to say this does not qualify as a function that can have an inverse. We say all that by simply stating that g is not a one-to-one function. When something is not a one-to-one function, it could not have an inverse, right? So g of x is not one-to-one. So g of x is not invertible, right? It does not have an inverse function. Does not have an inverse function, right? Unless, like I said, we could do some sort of a cool thing, maybe restrict the domain, maybe we specifically go out and like cherry pick one of these and cross it out from the domain. So if I, for example, canceled out the 2 from the domain here, I could say, well, g of x is one-to-one as long as we restrict the domain by canceling out the 2. Okay, that might work in some cases, but that's not where we're heading in this class. That's overly complicated. For us, we're just going to say, nope, this one doesn't qualify. Let's stay with the ones that do qualify as a function that can have an inverse. So symbolically, we would say this, g of 2, oops, let's go here. G of 2 is equal to g of 3, but 2 does not equal to 3, right? That's pointing out this very scenario here. Notice that g of 2, well, that's the 4, and g of 3, well, that's the 4 as well. They both equal to 4, therefore they equal to each other. That's what this is saying. G of 3, well, that's equal to 4. And, well, g of 2, well, that's equal to 4. Well, therefore, they're equal to each other. G of 3 equals to g of 2. But, clearly, 3 does not equal to 2. Right? So what this is pointing out is that we've identified this situation. We have 2 different unique values in the domain that are both leading to the same number, right? That's just what this is saying. Hey, pointing out that the 2 and the 3 both lead to the 4. Notice that we didn't actually identify the 4. We're just saying that they equal each other. They are both mapping to the same spot in the range, and yet they're not equal to each other, therefore not one-to-one, right? So this is how we can point out that we have a problem, and therefore g of x is not one-to-one. So we conclude thus, g of x is not 1-to-1. In general, this is the notation we adopt. So if something is one-to-one, this is the case. Functions that have this property are called one-to-one. That whenever that when we are looking at our function, that the outputs don't equal each other whenever the inputs don't equal each other. Right? That's what this is saying. And so here is the formal description of that. A function with a domain A is called one-to-one function if no two elements in A have the same image. That is, that f of x sub 1 does not equal to f of x sub 2 whenever x sub 1 does not equal to x sub 2. Okay, this presentation of this rule, I think, is a little bit more complicated than it needs to be. I've never really liked that style of presentation for it, so I don't really use it. This is mathematically equivalent to this one, and I think it's just a little more straightforward, right? So an equivalent way of writing the condition for a one-to-one function is that if f of x sub 1 equals f of x sub 2, then it must be the case that x sub 1 equals to x sub 2, right? So whenever you have, if you're focusing on the domain, let's come back up here. If you're focusing on the domain, right, and you notice that there are apparently two different results that are leading to the same output, if you can conclude that, oh, you know what, actually these two things are actually the same number, then you have yourself a one-to-one function. That's what this is saying. So do the jelly bean thing. So here's this thing. Here's the domain of f. Here's the range of f. So we're saying, oh, look, here is a unique value in the range of f, and it looks like something is being mapped from over here, from under the influence of the function f. Well, let me put a different color. Let's say that there is an x sub 1 over here, such that when I map it over under the influence of f, whatever f is doing, it lands as an f of x sub 1, right? And then there's this other one, apparently, x sub 2 over here. Here's x1, here's x2, and it also seems to land in the exact same spot. It looks like this is equal to f of x sub 2. So you might be thinking, oh, we found two different values in the domain, so that x sub 1 and x sub 2, so that when I apply the f function to both of them, they both seem to be leading to the exact same spot. Well, if you can show that whenever this is true, or if this is true, that you can confirm that, oh, you know what, they're not really different numbers. They're in fact equal to each other. X sub 1 equals to x sub 2. I know that looks kind of weird, but think of maybe somebody thinks that they're different numbers. Like maybe somebody says, look, when I plugged in a 10 over a 2 and I plugged it into my function, I got this value. And I came over here and then I plugged in a square root of 25. I plugged in square root of 25, but they're different, and then I got the same value, right? And you're like, oh, wait a minute. No, in fact, it turns out the 10 over 2 and the root of 25, they're both equal to each other. Oh, okay. And that must be true for every single value. If you can show that that's true for every single value, then you've confirmed that this function f is one-to-one. If you can find even just one number where that's not true, or one case where that's not true, where you really do find two unique values in the domain and they both lead to the same value in the range, then you have proven that that function is not one-to-one. This also gives us a nice formal way of proving that a function is one-to-one. This is the way you'll do it. You'll begin by letting f of x sub 1 equal f of x sub 2, and then using your equations and your using some math to then confirm that it must be the case that x sub 1 must then equal to x sub 2. Okay, but I don't think we have to do any of that in our homework. I'm not really sure. We'll look at seeing what the homework assignments have at the end. So if a horizontal line intersects the graph of f at more than one point, then we see from figure 2 that there are numbers x sub 1 that do not equal to x sub 2 such that f of x sub 1 equals to f of x sub 2. Okay, so when we're looking at the graph of a function, this blue line here, in some cases it's useful to think of it as a curve, like a curved line like this one. But in many cases it's useful to think of it as an infinite set of ordered pairs, right? There's just little ordered dots. There's just so many ordered dots that to the naked eye it looks like a smooth curve, but it's really a bunch of ordered dots. And every single ordered dot is a connection between an input, right? So let's say the input is A, or just to put a number, maybe the input is 7. Maybe this maps 7. And then the output connects this guy over here. Maybe the output is 11. So maybe this is the ordered pair 7, 11. And there's just an infinite number of them, right? So every single dot on here represents an input and an output. So if we have the function f described by this blue curvature, and we focus on this particular point where this red line intersects both of these, that means that this point on my curvature is the point x sub 1, comma, erase this, this point is the point x sub 1, comma, f of x sub 1. Right? So the input is x sub 1, and the output is f of x sub 1. It's equal to this height right here. F of x sub 1 is that height right there. It's this height there along the y-axis. It's this height here along the y-axis direction. And same thing over here, when we input x sub 2 into our function, we get to this height there. So that means that this point here is the point x sub 2, comma, f of x sub 2. Right? And by the way I'm describing it, it's going to have the exact same height. Right? That's why it crosses along with this red line. It's telling us that the line is also going to be equal to f of x sub 2. So what we have here is that this red line confirms one place where the function has the same outputs, f of x sub 1 equals f of x sub 2, f of x sub 1 equals f of x sub 2. However, clearly x1 does not equal x sub 2. So we have proven that f of x is not 1 to 1. F of x is not 1 to 1. Okay, so that leads to something we call the horizontal line test. A function is 1 to 1 if and only if a horizontal line intersects its graph more than once. I'm sorry, the horizontal line test, a function is 1 to 1 if and only if no horizontal line intersects its graph more than once. Right? So as we sweep up and down with this red line, if it ever touches our graph at more than one spot, then we have proven that that graph is not the graph of a function that is 1 to 1. If it only ever touches it at one point at a time, then we have shown that it is a 1 to 1 function. Right, so let me show an example. I'm going to use Desmos. It's a free online graphing site. You're welcome to use. So let's just throw a random polynomial here. F of x equals 2 x to the third power, or let's make it fourth power plus 2 x to the third power minus 5x plus 2. That's good enough. Okay, x to the fourth power plus 4x to the third power minus 5x plus 2. Let's change the color of this guy. Make it blue. Okay, so we can have this function given to us. and we might be given this graph, and we might be asked, is this the graph of a function that's 1 to 1? Is this 1 to 1? So this vertical line test says, let's let y equal. So I made this horizontal line here, and then I can create that as a slider that can range from, say, -10 to +6, like that. Steps of 0.2, maybe. And so now I can have this guy sliding up and down. So y equals to c means that at this point y equals to 2. And then as I slide it around, now this time y equals to -6.4. So I have a visual here of this sliding up and down. And so this is the vertical line test. As I sweep this line up and down, if it's ever the case that I have this, I have a case where the red line crosses my graph at more than one point, then what I have found is one place where two different inputs, in this case, this decimal input and this decimal input, both of them led to the same output of -3. So I have found at least one situation where two different inputs in my domain lead to the same output. This is not the graph of a one-to-one function. Right? We've established that. So that's what the vertical line test does for us. Okay, so for example, is the graph x equal to 3 1-to-1? Well, we can do the graph, right? If you remember the graph of x to the third power, just a simple sketching of it, it's going to look something like this. Better job of writing that thing. So this is f of x equals to x cubed. And if we think about vertical lines sweeping this way, it'll touch there. Another vertical line, as it sweeps, it'll only touch there. So as we sweep through up and down, we see that it only ever touches our graph at a maximum of 1 point at a time. There's never a case where it touches it at 2 points at the same time. Therefore, we've shown by the vertical line test that this function is 1-to-1. Right? Desmos will do a better job of illustrating that. So let's make this extra simple. This is just going to be x to the third power. Looks like that. And as we sweep our line up and down, we see that it never touches at more than one spot. Let's make it... okay, so we can come back here to Desmos, and we can change x to the power of 3, and here we have the graph of x to the power of 3, or x cubed. So hopefully that's a familiar shape. And then we can sweep around this vertical line, and you see it only touches it at one. It only touches it at one spot. Let's graph that spot, or let's identify that point. That should be c to the 1. But don't worry about how I'm getting this right now. We'll deal with that later. So this is equal to this. Label it. There it is. So here's the spot at which it's touching. So as we sweep it around, sweep it around, sweep it around, you see that it only ever touches it at one spot. The red line, the vertical line that goes up and down, the vertical line only ever touches the blue line at one spot at a time. There's never a case where two different points touch. Right? So by the vertical line test, we can confirm that x cubed is 1-to-1. So that's one way to prove it. Graph it, do the vertical line test. Another way would be to just kind of rely on your understanding of the curvature and note that, here's one of the solutions. If x sub 1 does not equal to x sub 2, then x sub 1 cubed does not equal to x sub 2 cubed. So just knowing the nature of the curvature and knowing that two different numbers cannot have the same cube. There's no way that two different inputs will result in the same output, right? And that just kind of stems from understanding the graph in some very, very simple cases, or if you can visually see the graph, right? If it's presented to you, then you can use that logic. Otherwise, the graph and the vertical line test does a good job. Okay, so no horizontal line intersects the graph. That's what we did. So x cubed is 1 to 1. Note that this is a case where the function is always increasing, right? If you were on a roller coaster and you were heading up this way, you would always be increasing. Even here, you're increasing, but maybe it's slowing down, and then it starts increasing again, increasing again, right? But you're always going up, right? If this was your salary, it's going up, it's going up, it's going up. Maybe there's a time when it's going up by a little less, but still going up. It never really reaches a point where it goes down, and it doesn't stay flat for a while. So it reaches there, and then maybe it starts going back up again. Maybe the rate at which it's increasing changes, but it's always increasing, right? So every increasing function and every decreasing function is 1 to 1. Right? It can be proven that this is true. We're not going to go through the process of formally proving it, but that's something that we can take away from it. And you can see why that is from this example of x cubed. Okay, the inverse of a function. So the definition, let f be a 1 to 1 function with domain A and range B, then its inverse function, and we adopt this notation right here with f with a tiny little -1 up in the exponent, has domain B and range A, and is defined this way. F inverse of y equals to x, if and only if, this double arrow thing interprets as if and only if, f of x equals to y. So this is true only if this is true, and this is true only if that is true. So one demands the other. They depend on each other. Both of them must be true. Okay, so think about the jelly bean diagram of what we're trying to do. We have some function f, and maybe we have the domain here, domain of f, and then it's leading you to some range of f, range on f. So every single value in here, so some value a that starts there, here's a in the domain of f, so a is going to map it over here, and it's going to take you to some value b, which is equal to f of a. So the a equaled b, right? B is the output of f of a. And then what happens is you come over and you take this output b and you plug it into the inverse function. So this is f inverse, and this is f. So these functions will undo each other, right? So what happens if you plug in a b? Well, it should take you right back into this a, right? Because they undo each other. So when we plug in b into this function, we should get that f inverse of b is equal to a. Right? So bringing those together, we have that f of a equals to b, and then it must be the case that f inverse of b equals to a. Good. Okay, well that's what this is, except that here they're using x and y, and I think math uses x and y way too much, to a point where it starts to become a little bit confusing because we use it so much. I think we add to the confusion of things by overusing x and y. Anyway, but that's what this is saying. So if the function f leads the input of x to some output y, and then we take the y and we plug it into the inverse function, it should bring us right back to x. And that should be true for any value in the domain of each one of these. Okay, so here's that same jelly bean thing with an x. So this definition says that if f takes x over to y, right, so here's this forward direction, it takes the x and it takes it over to y, this is the f function, so that we have f of x equals to y. And then we go backwards and we take this y and we plug it into the inverse function, that it should bring us right back to x. And so we should have that f inverse, when we plug in a y, it should lead me to x. Right? And so we have, bringing those two statements together, we have f of x equals to y, and its return trip, which is equal to f inverse of y equals to x. So we're saying that these two must be true, if and only if. This implies this, and this implies that. If you can do that for every single value in the domain, for every single x in the domain of f, and every single value y in the domain of the inverse function. Right? Notice the domains here. So A is the domain of f, right? Equals domain of f. And B, well, B is the range of f. But also, if we're going backwards, that means that this is the domain of f inverse. Domain of f inverse, right? The reverse function takes values from here and maps them back to here. So the range of f must be equal to the domain of f inverse. The range of f is equal to the domain of f inverse. And then going backwards this way, well, this must be the range of f inverse. Range of f inverse. The range of f inverse equals the domain of f. Okay, so it must be true that the domain of f equals the range of f inverse, and that the range of f is equal to the domain of f inverse. And it must be true that this round trip takes place for every single value x in the domain of f, and every single value y in the domain of f inverse. Right? If that's true, then you have two functions that are inverse functions of each other. Right? These two operations, whatever those instructions are, really do undo each other. Here's another little example with some numbers. So let's say that these two functions, f and f inverse, are defined this way. We have that f of 1 leads to 5, f of 3 leads to 7, f of 8 leads to negative 10. And then they ask us to find each one of these other guys. So let's map them. So doing the jelly bean description of what we are given, we have that under the f function, let's call this domain of f, and this the range of f. We have that the number 1 is in here, and it maps me over to 5. And we have that the number 3 is in here, and it maps me over to 7. And I have that the number 8 is in here, and it maps me over to negative 10. Right, so this is what's happening with the f. F function applied to 8 leads to negative 10. The f function applied to 1 leads to a 5. The f function applied to a 3 leads me to a 7. Okay, so now they are asking us about the inverse function. So the inverse function will then have to be a round trip. So inverse of 5, well, if things are working out properly, when we input 5 into the inverse function, the reverse function, it should lead me back to 1, right? So just by its description, by its very definition, f inverse of 1, f inverse of 5 must be equal to 1. And f inverse of 7, we go backwards here, f inverse of 7 must map me back to 3. And finally, f inverse of negative 10 should lead me back to 8. F inverse of negative 10 should lead me back to 8. Right? That's by the definition of what an inverse function does. If it didn't do that, if this wasn't true, if it turned out, oh no, this is wrong, f inverse of 5 doesn't lead to 1, well then this wouldn't be, these two would not be inverse functions. Right? By their definition, it must be true that they do this. Okay, so that's what I wrote. F inverse of 1, f5 equals to 1 because f of 1 equals to 5. F inverse of 7 equals to 3 because f of 3 equals to 7. And f inverse of 1, f inverse of negative 10 equals to 8 because f of 8 equals to negative 10. Okay, so it's the same thing I did. Let's move on. Okay, don't make the mistake. The negative 1 in the f inverse for the exponent does not mean this, right? So this is a very, very common source of problems with people, and there's really very little we can do about it, right? So nobody sat down and invented math, right? We didn't sit down somewhere and create it. It's the result of thousands and thousands of people across many generations, many cultures, many languages. People come up with ideas, and many of them just kind of flourish for a while and maybe go away. Maybe they're proven wrong. But some of them kind of last the test of time and then hand it down from one generation to another generation. And then people pick up what their ancestors gave them and add to it and improve to it and maybe add new ideas or a better way of describing the idea. And so notation becomes a real big issue. Having said all that, in algebra, we just finished talking about that little negative in the exponent. So if we had 3 to the negative 2, this little minus right there means that we can rewrite it underneath the function like this to a positive 2, right? Which is equal to 1/9, right? So if you want 1/9 of a pound of turkey and you go to the grocery store, give me 1/9 of a pound, you can also ask for 3 to the negative 2nd pounds of turkey or whatever, right? So they both equal the same thing. Okay, but it does not mean the same thing with functions. So if we had a variable, x to the negative 1, then that would also mean this, right? To the positive 1 or just to the x. True, right? So these are true. True. But now we invented this whole new idea that f to the negative inverse like this in function notation, this does not equal to this. It does not mean that what we have to do is flip it underneath 1 to get rid of that minus. It does not have anything to do with that. We just invented this notation so that we can identify that two functions are connected in that they undo each other. They're inverses of each other. Okay, that's all. So keep that in mind. So by definition, the inverse function f inverse will undo what f does. So if we start with x, apply f, then we apply f inverse, we arrive back at x where we started. Right? So if we take any starting point in the domain of f, shoot it over to the range by applying the f function, and then we take that output and plug it back into the inverse function, it'll bring us back right where we started, right? It's a round trip when we apply both the f followed by the f inverse, or the other way around. So in general, any function that reverses the effect of f in this way must be the inverse of f. Okay, so this is how we can prove that two functions are inverses of each other. So let f be a one-to-one function with domain A and range B. The inverse function, f inverse satisfies the following conditions. F inverse of f of x equals to x for every x value in A, and f of f inverse of x equals x for every value in B. Conversely, for any function f inverse saying the same equations is the inverse of f. So if this is true, if we can show that this is true, this is how we can show that f and f inverse, right, these two functions are in fact inverses of each other. So let's see. Let's do an example. Let's do a simple example. For example, let's say we know that f of x is equal to 3x plus 4. And let's just, for a moment, call it g of x, because maybe we don't know that it's the inverse function. It would kind of defeat the purpose if we start off by saying this, I think, because, well, the fact that you're writing it this way, you're already pointing out that they are inverse functions, but maybe you don't know, right? So maybe you have this function, and then they give you this other function, x minus 4 divided by 3, and they're asking you to confirm it. You know, are these functions inverse functions? Are f of x and g of x inverse functions? Question mark. Okay, so what we want to do is take some value in the domain, plug it into this f function, and that'll lead to some value in the range, right? So using my little jelly bean things, what I'm going to do is I'm going to start off with some value. Well, let's put it in blue. I'm going to start off with some little value here, some arbitrary value in the domain. I could use x, but as I said, we use x way too much, so I'm just going to use a. So let's say a is in the domain of the f function. So given a as a member of the domain of f of x, then I'm going to plug it in. I'm going to get f of blank equals to 3 times blank plus 4. And the thing I plugged in was that a. There it is. And, well, I mean, I don't know what the value of a is. A is something in its domain, so I can't really simplify it any further. So that's where it leads to. It leads to 3a plus 4. 3a plus 4. Whatever that is, that's the output where it leads to when I apply f to that. Okay, now what I want to do is I want to take this and I want to plug it into the g function. And if I can show that when I plug it to the g function, it brings me back to a, that the set of instructions for g bring you back to a, then I'm halfway there to showing that these two are actually inverse functions of each other. They undo each other. Okay, so I'm going to take this guy here and I'm going to plug it into there. I have my g of x function. Says g of blank equals to blank minus 4 over 3. And that blank is going to be the 3a plus 4. 3a plus 4. When I plug in 3a plus 4, well, the plus 4 and the minus 4 are going to cancel. And then I'll be left with g of 3a plus 4 equals to 3a over 3. And then the 3's cancel. And so I've shown that the g function is going to reverse the process and bring me back to a. So I started at a, the output was 3a plus 4. And then I took that entire output and I plugged it into the g function. Under the g instructions, whatever the input is, I'm going to subtract 4 and divide by 3. So I subtract 4, divide by 3. And those instructions will undo these instructions and bring me back to a. So I'm halfway there. Now I want to go backwards. Now I want to say, well, now what if I had the reverse? I'm going to start off with some value over here, some b value in the g function, and I'm going to plug it into the g which means it's going to be equal to b minus 4 divided by 3 will be my output. And then I'm going to come in here and I'm going to plug in that into my f function. I'm going to plug that into my f function, and hopefully it'll bring me back to b, right? So this is what I want to do. So I want to say now I'm going to let b be some member in the domain of g of x. So then g of b is going to be equal to b minus 4 over 3. And well, there's nothing special there. It's just going to be a b and a b. So it's just going to be b minus 4 over 3. And then that's what I want to take and plug into my f function. So now I want to take f of blank. And now the instructions for the f are to triple it and add 4. So it's 3 times blank plus 4. And that blank is going to be this entire thing. So I'm going to plug in a b minus 4 divided by 3. B minus 4 divided by 3. And now the 3's cancel. And I'm left with a b minus 4 plus 4. And now the 4's cancel. And I'm left back to b. This brings me back to b. Okay, so what I've accomplished is that I started with b over in the g. The first thing I did was to start with something in the domain of g, and I plugged it into g. That led me to this, and then I took that whole thing and I plugged it into the f function, and it brought me back to b. So I've shown that in both directions I have a round trip. In both cases, these two operations undo each other. So by this description, I have proven that g of x and f of x are inverses of each other. And in fact, to show the world that they are inverses of each other, we like to use the notation with a little minus 1, right? So we've proven that we have proven that f of x and g of x are inverse functions. Thus, we can say that g of x is actually the same as this little minus 1 like this. Just so that the world knows, just the notation style we adopt to let people know that g and f are inverses of each other is that we use that little notation. Otherwise, how would people know, right? If we just have f of x and g of x, people might not know that they're inverses of each other. Okay? All right, so we'll look at some homework problems, and we'll do maybe we'll do something like this, where they're often just given to you. So we'll look at some homework problems where they often just give you the f and the f inverse, and they're just asking you to prove that they're inverse functions of each other. Okay, so finding the inverse function. Well, this one's a little bit different. Here, they're not asking you to prove that two functions are inverse functions of each other. They're going to be asking you to find it, right? So given a function, find its inverse function. So let's examine how we compute the inverse functions. We first observe from the definition of inverse function that y equals to f of x if and only if f inverse of y equals to x. So if y equals f of x and we are able to solve this equation for x in terms of y, then we must have that x equals f inverse of y. If we then interchange the x and the y, we have that y equals to f inverse of x, which is the desired equation. Okay, so what does that mean? It just gives you a little framework, little rules that you can follow in order to find the inverse function. So here are those little rules. We're going to start with the given equation and make sure you solve for y. So rewrite it in the form of y equals instead of f of x, right? So get rid of function notation. Y equals f of x. 2, We're going to solve this equation for x in terms of y, if possible. 3 interchange x and y, and finally the resulting equation y is equal to f inverse of x. So what I like to do is this. I like to do this step first and then this step second. So me personally, I like to do this as step number 2. And then this as step number 3 myself. And then this is the final part. The resulting equation is this. Okay, so let's solve it for this one, and then we can do a step-by-step process and see how this applies to this. Okay, so step number 1 is to let y equal to f of x. So find the inverse of this function. F of x equals to 3x. Okay, step number 1, let's write them over here. Step number 1 is going to be to let y equal to f of x. Okay, well, that means that I just need to rewrite it this way. Oh, let's get rid of the red. Red's annoying. Okay, let's write it up here. Number 1, we're going to let y equal to f of x, right? So get rid of the function notation. That's what step number 1 says. So all we have to do is rewrite this as y equals to 3x minus 2. Okay. Next, I want to interchange the x's and the y's. Step number 2, interchange x's and y's. That just means go through your equation. Whenever you see an x, you're going to write it as a y. Whenever you see a y, you're going to write it as an x. So y equals 3x minus 2 is going to be rewritten as x equals 3y minus 2. The reason I like to do step number 2 before this one is that now we can solve the equation in terms of y, right? We're used to solving for y, so that way we stay consistent, right? We like to solve for y. So step number 3 is going to be to solve for y. So this one was interchange x and y. And now we're going to solve for y. Solve for y. That's pretty easy, right? All we have to do is add 2 to this side, add 2 to that side. I'll end up with x plus 2 equals to 3y. And next I want to multiply both sides by 1/3 or divide by 3, same thing. So 1/3 times all of it, not just the first term, all of it, which is the same thing as divide the whole thing by 3. So we end up with x plus 2 divided by 3 equals to y. And then finally this. Once you've solved for y, that means that that is your f inverse function in terms of x. So that's the last step here, to recognize that it must be that f inverse of x is x plus 2 over 3. That's how we can find the inverse function of that function. Okay, not bad. In fact, when they're really easy, like in this case, I think you can easily find the inverse function without having to do this process, but it's nice to have that process in place for when they get more complicated. But in this case, notice that it probably wouldn't be hard to find the inverse function, right? So another way we could do this is to write down the instructions of what we're doing here. The f of x function, what does it do? It takes the input, and the first thing you have to do, following the order of operations, is to multiply by 3. Multiply the input by 3. And then once you have that, you're going to take the result of that product and subtract 2. Subtract 2 from the results of step 1. Right? Whatever you get from step 1, subtract 2. Those are these set of instructions. And now the inverse function, well, paying attention to the definition of it, right? The inverse function is going to be a function that will undo this process. So The reverse of subtracting 2, is going to be to add 2. And the reverse of multiplying by 3 is going to be to divide by 3. And not only do we have to undo each one of these steps, we have to undo them in reverse order, right? It's like a knot that you have to undo the knot. You go from the outer and work your way in. So for the inverse function, the first thing we want to do is undo this one. And so the opposite of subtract 2 will be to add 2. Add 2 to the input. And then step 2, the opposite of multiply the input by 3. The opposite of multiplying by 3 is to divide by 3. Divide the results of step 1 by 3. Right? That's the opposite of this. So this will undo that, and this will undo that. And now if we think about a way to describe these set of instructions, the input plus 2, okay, x plus 2, and then the result of that, right, whatever we get as a result of that, we divide that by 3. That's what this is. So there you go. F inverse of x must be equal to this equation. Okay, when they're really easy like this one, it's easy to come up with it, but they do get very complicated, and it can become overwhelming to try and just come up with it this way. So that's when this set of instructions becomes useful. So if you follow the examples in the book, you will follow it using these set of instructions. The book follows this, the author follows this. So we write y equals to f of x, solve the equation for x in terms of y, solve for x in terms of y, and then interchange the x and y, and then that's when you get to your answer. But I like to interchange the steps a little bit this way. So step 1 would be to replace the f of x with a y. Step 2 would be to interchange the x's and the y. Step 3 would be to solve for y, since we're happy to solve for y if you can. If it turns out that you can't solve for y, then there is no inverse function, right? That might be when you realize, oh, wait a minute, this thing does not have an inverse function, which probably means you didn't start off with something that was 1-to-1. Okay, so solve for y, and then when you're done solving for y, that is your answer. So let the y equal to f inverse of x, and that's your answer. Okay, so this is what the author did. Same thing. So a rational function is a function defined by a rational expression. In the next example, we find the inverse of a rational function. Okay, so find the inverse of this one. See, this one's a little bit trickier. It's hard to do it by writing down the order of steps. That can get a little complicated. You can still do it that way, but it's complicated. So instead, let's follow our procedural steps, right? So number 1, step 1 is going to be to let y equal to f of x. It's the easiest step. So step number 1, do that. So I'm going to let y equal to 2x plus 3 divided by x minus 1. Good. Step number 2 is going to be to interchange x and y. So everywhere you see a y, we're going to write in an x. Everywhere you see an x, we're going to write in a y. So x equals to twice y plus 3 divided by y minus 1. And finally, the hardest one, solve for y. Not finally, the next one. Solve for y. Solve for y in terms of x. So we want to end up with y equals something that has only x's in it. Okay, so how do we do that? So we have x equals 2y plus 3 all over y minus 1. So what I want to do is multiply both sides of the equal sign by the denominator, y minus 1 times y minus 1. On the right-hand side, these guys cancel. And what we end up with is a y minus 1 times x is equal to 2y plus 3. Then we're going to distribute. So distribute, distribute. And we end up with an x, y minus x equals to 2y plus 3. Don't lose sight of the fact that our goal was to solve for y. Here's our y's. I want to solve for y. So let's put everything that has a y on one side of the equal sign, everything that doesn't have a y on the other side. That way we can factor out a y, and that'll help us get it. Okay, so I'm going to subtract minus 2y on this side, minus 2y on this side. That'll give me x, y minus 2y. They're not like terms, so I can't combine them. Minus x equals to 3. And then I'm going to add x to both sides. Why am I doing this? Because it doesn't have a y. I want to get all the terms that have a y on one side and everything that doesn't have a y on the other side. So I end up with xy minus 2y equals to 3 plus x. And now this is when we notice that we can factor out a y. Both of these terms have a common term of y. So let's get y factored. We'll end up with x minus 2 equals to 3 plus x. And now we want to divide both sides by this quantity. So let's divide this side by x minus 2 and this side by x minus 2. And what we have as a result is y equals to, and I'm just going to flip these around. That's going to be x plus 3 divided by x minus 2. Okay. So, and then the last step is to let f inverse of x equal to y. Because you're done. That's our answer. F inverse of x is x plus 3 over x minus 2. Okay, so we're saying that these two functions are inverse functions of each other. How do we know that? Well, let's write them down over here. So we have f of x equals to 2x plus 3 over x minus 1, right? 2x plus 3 over x minus 1. And then we have that f inverse of x is equal to x plus 3 over x minus 2. How do we know that these two really are inverse functions of each other? Well, let's check it for one unique value. Just that won't be a proof, but that'll just kind of help us confirm it. How about let x equal to, let's see, let x equal to 3. So that means that we have f of blank equals to 2 times blank plus 3 divided by blank minus 1. So we're going to start off at x equals to 3, put a 3 there, put a 3 there, put a 3 there, and that simplifies to f of 3 leads to 6 plus 3 makes it 9. 9 divided by 2. Okay, so now we take that guy and we plug it into the inverse function, f inverse of something, and then we have something plus 3 divided by something minus 2. And so we're going to take this guy and we're going to plug it right into here. And if it works out, these two operations will undo each other and we'll come back, we'll end up right where we started. We should come back to 3 over 2 there and a 9 over 2 there. Okay, to simplify this guy, we're going to multiply the numerator and denominator by a giant 2, which needs to be distributed. And then that'll multiply to this guy, multiply to that guy, multiply to that guy, multiply to that guy. So we'll get that f inverse of 9 over 2 is equal to a fraction where the numerator has a 9 plus a 6, and the denominator has a 9 minus a 4. which leads to 15 divided by 5, which equals to 3. Right back where we started. Okay, that doesn't mathematically prove that this works, but at least it gives us some confidence that I showed that it worked for one unique randomly selected value, x equals to 3. So how do we do it in general? Well, instead of letting x equal to 3, we're going to have to let it be equal to some variable. So in general, we want to show that whenever we start off with let x equal to a, which is a member of the domain of f, we want to say that when we take f of a, that'll lead us to some output, right? We start off with a, we apply it to f, that takes us to some output, and then when we take that and we plug it into the inverse function, that it brings me back to a. And I also want to show the reverse is true, that if I start off with some b, which is a member of the domain of f inverse, that if I plug in b into f inverse, I'll get f inverse of b, and then you take that output and you plug it into the f function, and that it brings you back to b, right? We want to show both of these are true. Good. So, remembering the equations of f and f inverse are those. So here I want to show that f inverse of f of a. F of a would be to replace each of these x's with an a. So that would just be equal to, let me put it in blue, that would be equal to 2a plus 3 divided by a minus 1. I want to show that when I take this equation, right, this is the output of a. When you plug a into f, you get this. This is the output. Now you take that output and you plug it in f inverse. I want to show that these two operations will bring me right back to a. And the reverse is true. I want to show that if I take the value b and I plug it into the inverse function, that's this one, I'm going to get b plus 3 all over b minus 2. Put it in green. This will be b plus 3 over b minus 2. And I plug that into the f function, that it's going to give me a value of b. At the end of the day here, I'll come back to b. And that this is true for any value b in the domain of the inverse function, and that this is true for any value a in the domain of the inverse of the f of x function. Okay, so let me zoom out just a little bit. So looking at the instructions for the inverse function, I want to plug in this whole thing into the inverse function. Here are the instructions. Whenever you give an input, I'm going to have a fraction where the numerator is going to be the input plus 3, the denominator is going to be the input minus 2. So that means that this is going to be this guy, that will be 2a plus 3 divided by a minus 1. This guy plus 3 in the numerator divided by the same guy minus 2. 2a plus 3 divided by a minus 1, and then that guy minus 2. Okay. On the other hand, for the f function, these are the instructions. Given an input, I'm going to have a fraction where the numerator is twice the input plus 3, and in the denominator, I'm going to have the input minus 1. So that would be this input right in here. That would be b plus 3 divided by b minus 2. That's in the numerator, and then we need another copy it down here. It's going to be b plus 3 divided by b minus 2. And it's going to be a giant fraction where it's going to be equal to twice this input plus 3, and then this input minus 1. And I need to show that after all this magic here, if I cancel and reduce and combine and do my algebra, my goal is to show one, two, my goal is going to be to show that this will lead to A and that this will lead to B. Come down here. Okay, so how do I simplify this guy? Well, first of all, let's put a little 1 underneath there and a little 1 underneath there. That way I have addition of fractions in the numerator, addition of fractions in the denominator. And same thing over here. I can always put a little 1 there and a little 1 there, and I have nothing but fractions going on now. Okay, so let's simplify this by combining the numerator. In both cases, I'm going to simplify it by combining these two into one big happy fraction, these two into one big happy fraction, these two into one big happy fraction, and these two into one big happy fraction. So, erase this into space. I'm going to multiply this guy by an a minus 1 over an a minus 1. That way they have the same denominator. I'm going to multiply this guy again by an a minus 1. Well, you know what? Actually, it's even better if I do it the other way around. So I'm going to multiply the entire numerator of the fraction by an a minus 1, and then the entire denominator of this fraction by an a minus 1. And then when I distribute, and distribute, it should simplify this a lot. I end up with, I'm going to copy it just to make sure people are following. I end up with this times a minus 1 plus 3 times a minus 1 in the numerator. And in the denominator, I end up with 2a plus 3 over a minus 1 times an a minus 1 minus 2 times a minus 1. Right? I'm allowed to do this because a minus 1 divided by a minus 1 is just another version of 1. So that's allowed. And then over here, let's come back over here and do this one. Likewise, I'm going to multiply this numerator, this giant numerator, I'm going to multiply it by a b minus 2 divided by a b minus 2. That's another version of 1. I'm going to have to distribute. So it'll be this times this times that, and distribute here, which will be this times this, and this times that. So I end up with 2 times b plus 3 over b minus 2 times b minus 2 plus 3 times b minus 2 all over b plus 3 over b minus 2 b minus 2 times b minus 2 minus 1 times b minus 2. Okay, so luckily that means that these guys cancel. That means that these guys cancel. So over here I'll end up with 2a plus 3, that's the result of this, plus 3 copies of a minus 1 divided by 2a plus 3 minus 2 copies of a minus 1. So that's the result on that side. On this side, luckily, these guys will cancel, and these guys will cancel, giving me 2b plus 3 plus 3b minus 2 all over b plus 3 minus, parentheses, b minus 2. Okay, so then I'm going to distribute these guys, these guys, these guys, distribute, 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 and distribute. And hopefully the result is something that I like. So I'll end up with 2a plus 3 plus 3a minus 3. And I'll end up with 2a plus 3 minus 2a plus 2. Okay, and so now plus 3a minus 3a reduce, and I end up with 5a, and then plus 2a minus 2a cancel, and I end up with 5. So this ends up with 5a over 5. The 5's cancel, so I get exactly what I wanted. I get my a. Started out with a, ended up with a. Okay, on the other side, I'm hoping to end up with b. So this ends up being as 2b plus 6 plus 3b minus 6 all over b plus 3 minus b plus 2. And now the b's cancel here, plus b minus b. And 2b plus 3b is going to be 5b. The 6's cancel. And in the denominator, we end up with another 5. So we end up with, again, 5b over 5. And then the 5's cancel. And I end up with b equals b. Okay, zoom out. So I started off with b. I started off by plugging b into my inverse function, right, using the jelly bean scenarios here. Here is my b value. I started off with b, and then I applied it to the inverse function, f inverse, and that led me, f inverse, that led me to some f inverse of b, which is equal to this little equation. There's nothing else we can do to it, so it's just some f inverse value that's over here. And then I took that guy and plug it into the f function, and it brought me right back to b. Started off with b in the domain of f inverse. This is the domain of f inverse. And then it took me to some value in the range of f inverse. This value right here, mainly this one, b. So this one is b plus 3 divided by b minus 2. That's this point here. And then we applied that one into the f function. And then it brought me right back to b. Okay? So this initial step is so easy that it's really confusing, I think. People get very lost here because we start off at b, and when I apply it to the inverse function, well, this is all you get, right? That's the description of the f inverse function. So there's not much to it. So this is the output of the f inverse function. And then we take that and we apply it to the f function. And that's what this mess is, right? The instructions for the f function were to double the input plus 3 in the numerator, and then the input minus 1 in the denominator. And so that's why we get this. I should write them down here again. So again, just to remember, the instructions for f inverse of x are b. What? We should write them this way. How about instructions are blank plus 3 and blank minus 2. Right? I'm just going to put a highlighter here. Those are the instructions. It's blank or blank. Blank, the input goes in here, right? And then so blank plus 3, the input plus 3 divided by the input minus 2. Those are the instructions for f. And the instructions for f, for f inverse, and the instructions for f are that given an input, we're going to do twice the input plus 3 all over the input minus 1. Okay, let's put that in yellow. Here's the input. Do twice the input plus 3 all over the input minus 1. So that's what we did here. It's going to be twice the input plus 3 all over the input minus 1. So we applied this into the f function. And then we did a bunch of algebra and arithmetic and reducing, canceling, a bunch of stuff. And we showed that we started at b and then we ended up at b. Good. And then the reverse is also true. So this one's describing a case where we started off with a. A is starting off in the domain of f. So using this little jelly bean diagram over here. So we're starting off with some value a. Some value a in the domain of f. Domain of f. And we applied the f function into that value, and we arrived at some point over here in the range of f. And when we apply a into f, it seems a little silly because it's just going to be f of a, right? Just plug it in there. Since we don't know the value of a, we really can't do much with it. So this is, in fact, just that value of 2a plus 3 over a minus 1. This is 2a plus 3 over a minus 1. There's not much we can reduce there, so it's confusing because it's like, oh, well, all we did is replace the x with an a. True, there's nothing else you could do. But then the tricky part is this one. Once this is the output, the next step is to take this whole thing and plug it into the reverse function, the inverse function. So now we want to go backwards and take this whole thing right there and plug it into the f inverse function and hopefully show that it brings us, the f inverse function is going to bring us back to a, right? And keeping track of the pattern of f, here's our input. The instructions for the f inverse function are going to be to take the input and add 3, divided by take the input and subtract 2. And that's what we did here. Take the input, add 3, take the input, subtract 2. And then a bunch of arithmetic, canceling, distributing, a bunch of work later, we show that in fact we do arrive at a. Started at a in the domain of f. We traveled over to some output in the range of f, plugged that into the f inverse function, came back to a. So it's a round trip. Started at a, went to the range of f, plugged it back into the inverse function, brought me back to a. And then the other direction as well. So since we've shown both, that is proof that these two really are in fact inverse functions of each other. And that's what this is describing up here. We're looking at this table. So back to this, this description of an inverse function, we just use this to prove that two functions are inverses of each other. Right? The work I did is exactly what this is describing. Okay, moving on. Okay, so now graphing the inverse of a function. So the graph of f inverse from the graph of f. So if f of a equals to b, then f inverse of b equals to a, right? That's the definition. So again, with our jelly bean description of these, we have some sort of domain of f, and then that leads to some range in f. So if there's a little a here, then we plug it into there. Then it leads to some value b. Then we have an ordered pair a comma b, right? A comma b is in the f function. But now if we want to go backwards, that means we start there and we plug it into the inverse function. It takes us back, the inverse function, it takes us back to where we started, meaning that this is the domain of f inverse, and this guy is the range of f inverse. Another language instead of domain and range is input-output, right? And so if this is the way these work, then that must mean that the ordered pair B comma A is a point in the graph of F inverse, and A comma B is in the point of the graph of F. And that must be true for any 2 points in the domain and ranges of these functions, by definition, right? So the point A comma B is on the graph of F, if and only if the point B comma A is on the graph of F inverse. So if we had a table of values, right, this is saying, kind of in simpler words, hopefully, if we have a table of values where we have just inputs, outputs, and we just have a bunch of numbers, like let's say 3 maps to 7, and 5 maps to 11, and 7 maps to 13. We just have input, outputs. This leads to the ordered pairs 3, 7 on our graph. This leads to the point 5, 11 on our graph. And this leads to the point 7, 13 of our graph. So if we want to just think about the table of values for the inverse function, so if I have some sort of an inverse function here, x inverse of x, the inputs are going to be these guys, right? So 7 must lead to 3, right? Because it's the inverse, it will undo it. So 7 leads back to 3, 11 leads back to 5, and 13 leads back to 7. Therefore, the inverse function is going to have the ordered pairs 7, 3, 11, 5, and 13, 7. So a pattern, right? Math is all about patterns. The pattern we notice is that, okay, well, we could just switch these guys around. If we just flip the input and the output like this, then we get points in the other graph, right? So if we have a bunch of points in the function f of x, to find points in the function f inverse, we just switch these around. And when you do that, you establish a little pattern in its graph. So for example, let's go back to Desmos. Let's graph a bunch of ordered pairs. So let's say I had a table of values and it was just 1 and 3. There's an ordered pair right there. And let's say I had another table. Oops. Another table, which is 3, then 1, like that. So I get that point. And if we draw the line y equals to x in red, okay, so here's the line y equals to x, and here is the point 1, 3, and the point 3, 1. Okay, let's do a couple more and see if you notice the pattern. I'm just randomly picking these numbers. So let's say it's going to be say it's going to be 2 leads to 5. Okay, that's that point there, in blue. And then over here, if I just switch these around, because these are going to be inverses of each other, then I must have a 5 leads to 2. Okay. Maybe up here I have a 1 leads to 0. And so therefore over here, it must be that 0 leads to 1. I'm just flipping them around. Notice that in every single case, they are a mirror image across this line. This point and this point are a mirror image. So the distance across this is equivalent. Let's try a couple more. How about negatives? How about negative, if this is negative 3 leads to 3, then it must be the opposite, that positive, oops, I don't want that. I don't want that because it leads to a 3. How about leads to -1? Then it must be the case up here that negative 1 must lead to negative 3. Okay. I got 0 involved. Okay, sorry. So the pattern we want to establish is that in every one of these cases, if we think about the distance from each one of these points across this way, if we want to think about all of these points that go from there to there, from there to there to there, and there to there to there, and there to there to there to there, in every single case, the red line cuts that distance exactly in half. It's a bisector of the line segment that connects those 2 points. So this distance there is equal to that distance there. From there, well, I know, let's use a highlighter. So this distance in yellow is equal to this distance in green from there to there. And, well, it's really messy though, but I think you get the point. This distance from there to there is equal to this distance from there to there, and so on and so forth. So this distance from there to the red line is the same thing as this distance from the red line to the point, and finally same thing over here. So this will be consistent all the way throughout. For every single ordered pair, we'll follow this situation. Okay. So for every point A comma B, there will always be a point A comma B, right? Just kind of flipping around the A and the B, and so this pattern will exist. There will be a mirror image across the line y equals to x. And so as we continue to do that, we will see that the graph of f and then the graph of f inverse will be a mirror image about the x-axis. It will mirror each other. Let's try one more example with this up here. We established that these two functions were inverse functions of each other. Up here, we went through all this work. We went through all this work before to show that these two functions are inverse functions of each other. Let's graph both of these guys. First of all, on a point-by-point basis, and then we'll see once we finish that they're inverse functions of each other. So let's go back over here. Okay, so I have my graph y equals to x. I've established the first function, f of x here, and then I have f inverse here. So I can just randomly pick a couple numbers and see what happens. If I put in a 1 into my f function, that leads to this point, 0, comma, negative 3. That would be this guy right here, 0, comma, negative 3. Let's put it in red. It really pops out. Well, if I put it in red, then that'll be in red. That's fine, so we'll put it in green. So now I take this negative 3 and I put it in here, negative 3, negative 3, and then of course that leads to 0, so that'll be this point. And again, we established that property that if we draw a line that connects this point and this point, if we draw a line that connects them, the red line will be right in the middle. It'll bisect it, it'll cut it in half. Or you could say that the distance from this green point to the red line and the distance from this blue point to the red line are going to be equal to each other. Okay, so let's just do that for a couple more points. See that the pattern continues. How about for negative 2? Negative 2 leads to 0.333. Okay, that's 1/3. So let's put 1/3 over here. 1 divided by 3 leads to negative 2. Okay, so I have a couple more points. How about negative 1? Negative 1 leads to negative 1. Needs to negative 1/2. Notice that positive 1 is not a valid. It's not in the domain of this function because otherwise we'd be dividing by 0. So 1's not in there. How about 2? How about 3? How about 4? How about 5? How about 6? How about 7? About 8? Okay, so I'm getting a pretty good idea, a pretty good sense of what's happening with the blue function by plugging in a bunch of ordered pairs. Eventually, I'll plug in the equation and we'll confirm what all those points are. And then for the green one, all I have to do is flip these around. So I know that negative 0.5 is going to lead to negative 1. And I know that 7 is going to lead to 2. And I know that 4.5 is going to lead to 3. And then I know that 4.666666667 is going to lead to 4. And I know that 3.25 is going to lead to 5. And I know that 3 is going to lead to 6. And I know that 2.83 leads to 7. And I know that 2.714287-ish leads to about 8. Okay, so I have all of the green ones, all of the blue ones, right? So here's all the green ones, and then here's all the blue ones. And if I wanted to keep going and find more ordered pairs, eventually I'd find the whole graph. So let's just type it in and see what the whole graph looks like. So if I kept going with all those blue values, eventually it would look like this. And then if I think about a mirror image, a reflection about the red line, right? So maybe take it in pieces, maybe just focus on this top part. What would it look like if I did a mirror image of it, if I reflected it about the red line, right? The red is a mirror. What would it look like across of it, a mirror image across it? Okay, so if you think about that, let's get rid of the blues. So all the green ones look like this, and I can keep going. You can see sort of what the pattern is going to be. So if I copy this, copy, then back over here, I'm just going to call it G here. Get this guy. So you get something that looks very similar, and that's the green one. So now if we graph them both, hopefully we can convince ourselves that the and that mirror image property stays consistent, right? So here, let me copy this and okay. So it's a mirror image in the sense that if we look at this portion of the blue line, just this portion that goes up to there, then its mirror image across the red line would be this portion on the green one going over there, right? So this one goes this way, this one goes that way. And then the opposite is true for this portion of the green line. The green line goes this way, and then the blue one goes that way, right? Same thing over here. If we zoomed in a little more, we focused on this one. Let's think about if we think about this portion of the blue, its mirror image would then be this portion of the green one, starting from here and then going up toward this way, right? So this portion of the blue and this portion of the blue are the ones that are like a mirror image portion of themselves. And then you do the same thing with the other part. I don't know if this did a great job of highlighting it. So let's do one more real quick example. Let me get back to normal screen size. So if I just had a graph that looked like this, and here is y equals to x, and I was given some function that did this, say I did a function that did this, f of x, then the mirror image would be something that goes like this. So this part would be this, so this would kind of go like that, and then this would go across kind of like that, and then this one would go like that. Oops, that does not look good. This would go this way, and then something like that. Something like that. Keep in mind my drawing skills suck. So the green one would be the inverse function of x. Right? So that's what I mean by a mirror image across the line y equals to x. Let's go back to this thing. So this portion in blue, coming from there to there, its mirror image across was this portion in green. So this portion and this portion are a mirror image of each other. And then this portion of the green and this portion were mirror images of each other. And then this portion and then that portion were mirror images of each other, right? Okay, so hopefully that does a slightly better job of identifying what I mean. 1 and x. Okay, one more simple example. Sketch the graph of the square root of x minus 2. Use the graph of f to sketch the inverse of f, and then find the equation for f inverse. Okay, the square root of x minus 2. This is going to be the same thing as the square root of x shifted to the right by 2 units, right? So think about the new 0. It's the square root of x, except the 0 has been shifted. The new 0 will occur when we input a 2, right? 2 minus 2 is 0. So this graph will look something like this. Here it is, and it goes, let's put it in blue. It'll look like this, root x minus 2. And then we think about this guy, which is the line y equals to x. And so therefore, the mirror image will be something that comes over here and goes that way, sort of. Right? So this would be the inverse function if this is the f function, f of x. Okay. We can do a better, I can do a better job of that with Desmos. So let's do Desmos. Let's get rid of all of this, all of that, all of that. That. Okay, here's my line, and then I have f of x equals to square root of x. Let's put it in blue. Okay, so here is the square root of x function, but then it's been shifted over to the right by 2 units. So let me shift it that way. So then the starting point here, oops, 2 units. So then the starting point there is 0, 2. And its inverse function is going to be a graph which reflects about the line y equals to x. So if the point 2, 0 is in the function of f of x, its inverse function is going to start off at the point 0, 2, and it's going to have a shape that reflects this way. So unfortunately, I'm going to have to cheat a little and type in the equation. So if this is f of x, I'm going to define f inverse, it likes f inverse of x as x to the second power. It does not like that, so I'm going to have to get rid of that. Oh well, I'm just going to have to label g. Plus 2, but it's restricted, so restricted for x being greater than or equal to 0, curly bracket. So I want to restrict the domain, and let's make it the color green. Green. There. So that's what I was attempting to do. So this is the same thing, only better. Copy that. So if this is f of x equals to the square root of x minus 2, then this must be the graph of the inverse function. Inverse f of x must be this one. And notice that it's a mirror image across the line y equals to x. Okay, so next let's find the equation for f inverse of x. If you were paying attention to the way I was typing it into the Desmos program, you already saw that I wrote the answer. Let's pretend you didn't see that. And how do we find it? Let's go through our step-by-step process. So, given that we have f of x equal to the square root of x minus 2, remember the step-by-step process. Number 1, we're going to rewrite this away from the function notation style and rewrite it as y equals to the square root of x minus 2. Note the domain and range here. So note that this is valid for x being greater than or equal to 2. Right? I can't input anything that is smaller than a 2, because then I'll end up with a negative inside the square root, and then that leads to imaginaries, and we don't want that. So x has to be greater than or equal to 2. And note that no matter what value you choose, once you input the valid numbers for x, the outputs are always going to be positive numbers, right? It could be anything starting from 0 on up, but you're never going to get a negative. So y is always greater than or equal to 0. So keep that in mind as the domain and range. Okay, so now let's follow our steps. Step 2 is going to be to interchange the x and the y. So I'll end up with x equals to the square root of y minus 2. Step 3 is going to be to solve for y. So I'm going to take x equals to the square root of y minus 2, and I'm going to square this side and square that side. So I'll end up with x squared equals to y minus 2. And finally, I'm going to add 2 to this side, add 2 to that side, and I'll end up with x squared plus 2 equals y. That's the third step. So write f of x as y, interchange the x's and y's, solve for y, and then the fourth and final step is to replace the y with f inverse of x, because you're done. That is the equation of f inverse. But keep in mind that if this was the domain of the original function, domain of f of x, and this was the range of f of x, that means that these things switch around. That means that for the inverse function, the range and the domain have flipped, so this will be the domain is going to be equal to x is greater than or equal to 0, right? The input is going to be the range of this one, and the range is going to be equal to the opposite, which is going to be y is greater than or equal to 2. Okay, so that's why we get this answer. That's why we get this graph. It's the graph of x squared. This is just a nice parabola. X squared plus 2 has been shifted up by 2 units, And then if we keep the restriction in mind, the domain only allows an input of x greater than or equal to 0, and the outputs are from 2 to infinity. And which is the reverse of this function, where the domain is from 2 to infinity, and the outputs are from 0 to infinity. Right, hopefully that's clear. Let's see what the author did. Okay, so those are the two graphs, the graph of f and f inverse. And then we get our equation from there. And so we get that. Okay, applications of inverse functions. So at a local pizza parlor, the daily special is $12 for a plain cheese pizza plus $2 for each additional topping. Find a function f that models the price of a pizza with n toppings. Okay, this should be nice and easy. So part A, we're looking for a function of f that models the price of the pizza, so as a function of n. So f of n is what we're looking for, where the input is n, the number of toppings, and the output is going to be the price. Right? So we input toppings, and the output would be price. Okay, so f of n, the price, well, it's $12 for a plain cheese pizza plus $2 for each topping. So I think it doesn't take much to realize that the answer is going to be $12 plus $2 times n. Or if we just flip it around, this is going to be equal to 2n plus 12. Part A. Part B says find the inverse of the function, and what does f inverse represent? Okay, so then for part B, let's put part B over here. Again, following those steps, we're going to let y equal to 2n plus 12. Why y? Let's use p for price. So the price equals 2 times the number of toppings plus 12. So step 1 is to get it away from function notation. Step 2 was to interchange the letters, so that it'll be n equals to 2p plus 12. Step 3 was to solve for the opposite, right? So instead of solving for p, we're going to solve, to solve for p. So next we're going to, that's step 2. Step 3 is to solve for p. Right? Normally we have y and an x, and then we interchange and still solve for y. Okay, so then we subtract 12 from both sides. N minus 12 equals to 2p, divide both sides by 2, and we get n minus 12 divided by 2 equals to p. And then we rewrite it in the inverse notation. F inverse of n equals to n minus 12 over 2. And for the letters to be meaningful, okay, so here we input toppings and out comes the price. In this case, this guy is going to be the price, and out will come out the toppings. Right, since this one is toppings go in, price comes out. Here we input the price and out come the toppings. So in this situation, when we have a word example where the letters are meaningful, it would be better to leave it with the letter P instead of the letter N. Right? In the previous cases, we switched it around because we have this, I don't know, desire to always express all functions where X is the input and Y is the output. So just to be consistent with that, that's why we do this flipping of the letters. That way, we always end up with a function defined with X as the input. But in this case, there's no need to constantly keep the N as the input. It doesn't make any sense. So rather than write it this way, which is perfectly okay, we can use any letter, right? I mean, they're just letters, they're dummy variables. Nothing wrong with switching it around to any other letter. So I can use, to express the exact same idea, any other letter, right? This is just saying, given an input, subtract 12 from the input and divide it by 2. That's what that says, right? So I can use any other letter. F inverse of A equals to A minus 12 divided by 2. Same thing. Or F inverse of Q is equal to Q minus 12 divided by 2. Same thing. So why not keep the P, right? So in this case, why not go for saying that it must mean that F inverse of P equals to P minus 12 divided by 2. Okay, so I hope that doesn't confuse you too much. Stick to having the letter there. Okay, and as we said, this is going to be the opposite. So we input a price, and out comes the toppings, and that's the explanation of what this is, right? The inverse function is going to be a function where you tell me the price that somebody paid, and I can tell you how many toppings they had. So for part C, we can use that function for that purpose. If a pizza cost $22, how many toppings did it have? So if P equals to 22, I can plug it into here and get that F inverse of 22 is going to be 22 minus 12 divided by 2, which means that F inverse of 22 is going to be equal to 10 divided by 2, or F inverse of 22 equals to 5. 5 toppings. Right? This is money, this is the price you paid, and then we plug it into the inverse function. We're able to get the toppings. Price is the input, toppings is the output, right? And we can just confirm that by going back to the original function where you plug in the toppings, and toppings, and we know that the equation is just going to be 2 times n plus 12. Oops. So f of n equals to n plus 12. So if we plug in 5 into here, f of 5, it's going to be equal to 2 times 5 plus 12, which means f of 5 equals to 22. So it's back to this guy. Okay, hopefully that makes sense, and that should be enough to cover just about everything in this section, I think. Okay, so let me know if you have any questions.